Thanks for the intro. My name is Syed and this is Trevor. We both work at PSI Quantum. Not sure if you guys are familiar, but it is a quantum computing company. And today we're going to be talking about quantum chaos and error correction. Yeah, so Trevor, you want to talk?
Yeah, I'll take it away.
Good.
How do I get to it next?
Okay.
Okay, yeah, so I'll just go over kind of the history of quantum
you guys
computing.
also have this if you want. You can click on tech events, baby.
Okay, yeah, this will be a bit off the cuff, but we like it that way. So I'll go over kind of like the history of quantum computing and then kind of define what a quantum computer is a bit. And Syed will take it away from there. So kind of in like the early 1900s, we have like some of the goats of physics, Planck, Einstein, Schrodinger, Heisenberg. They come up with quantum mechanics, which is one of the most, if not the most successful theory of science. It's been empirically tested like so much and to high precision. Then kind of in the 1980s, there's a really famous conference where this, another goat of physics, Richard Feynman, was like, oh, we should probably make something called a quantum computer that will speed up quantum chemistry simulation. Yeah, you can't hear me? Oh, sick. Okay. Sorry about that, guys. Yeah, so like, there was this famous conference and he was like, oh, the quantum chemistry, it's in batteries, pharmaceuticals, like everything needs it, transistors, and we can speed all of that up by running those simulations on a thing that's actually quantum mechanical, called a quantum computer. And then kind of, that was a pioneering statement. And in the 1990s and early 2000s, we started seeing some companies that were like, oh yeah, let's develop this thing. And kind of like the canonical way to do it is a quantum computer is just basically the switches of the computers, the zeros and ones are quantum systems. And you just trap an atom in a box and it computes for you. And like the atom does the zeros and ones, and if you can do this, and it's very hard, you can have some crazy shit happen. So with like a classical computer, transistor-based, with like 4 transistors, you have 4 bits. You have 1011 you can hold. With 4 qubits, so 4 quantum systems, which is the equivalent in a quantum computer, you can hold 2 to the 4, so 16 states. And you can imagine if you go to just 256 qubits or quantum systems, like trapped atoms, for example, you can hold a number that's 2 to 256. That level of solution space, and that number is bigger than the number of atoms in the universe. So that's the level of solution space you're wielding, which is 256 quantum systems. So that gives you some crazy computational properties. But one of the problems is having a bunch of these quantum systems together, they don't like to interact with each other. And the more you put together, the more errors that happen. And error correction is huge. And the holy grail of quantum computing is this thing called a fault-tolerant quantum computer. No one has it. The state of the art is Google has a 3-qubit fault-tolerant quantum computer. All this like headlines about thousands of qubits, they're shitty qubits. They're not error corrected. The state of the art is very low amount of qubits because the holy grail is fault tolerant, no errors, that has business value. And for that you need around 1 million shitty qubits because you need that redundancy in order to have good qubits. And with that, I'll bring it to Syed, who will talk about error correction and what they do to correct for these errors.
Yeah, I really hope I can make it as engaging as you did. Yeah, so I guess the question that comes after this is, how do we know something is wrong? Like, what is an error? And that's not a rhetorical question. Like, can someone from the audience tell me, like, what is considered wrong in your eyes?
If it's not true.
Okay. Yeah, if something's not true, that's a good answer, I think.
Math.
Math. Yeah, that's always a good answer.
Thank you.
Yes.
It produces results outside of like what you predict.
Results. I guess you could also argue like hallucination is like a result as well, right?
Yeah.
So that's like one element of like an error that we think could be true or false. I guess that's like what we're trying to find out, right? We're trying to find out what are errors in our code, and I think it's a mixture of everything. It's about results, about truth, it's about structure, and what reality is, and that's what we're trying to find out with error correction. So there's a picture I took off Google, and on the left, you can imagine the center dot is a qubit, and the boundaries are the measurements around the qubit. And so this is a way that we could look at a qubit and say, okay, this qubit doesn't have any errors on it, and this qubit does have errors on it. Of course, there's many different ways that this could take shape, but as an example of, okay, you applied an operation, and the result of that operation is not what we think is what reality should be. So what's one way for us to detect errors in a quantum computer? And this is a very, like, we were talking about this last night, but this is a very, like, contrived way of finding errors and finding a solution, but this is called a Blossom algorithm. And so from left to right is the different steps that this algorithm takes on a set of physical qubits to find what is the, errors in that set of qubits. So on the left, you can see that like this plane in the back is the detector graph, and on the left, there's like some detection event that happened that shows an error. And similar to like what I showed in the previous slide, like you can imagine it just detected one of these things that expected that, but this one came out. And so then what it does is, starting from there, it starts looking at the next error that's in that plane of qubits. And so it keeps running these steps to eventually find what is the path between these errors, and it will create this graph that you can then use to correct those errors. So that's a very like layman's demonstration. I think if there was like an expert, they'd probably be like, this is bullshit, but I think this is like good enough for the average person. So enough like gibberish. We made an example. Application for us to try out. So if you scan this QR code, it will like plop you onto a put you onto like a set of qubits. You will be a qubit, and we'll see how errors propagate.
All these eyes. These are people who are streaming.
Okay. So when we tested this out last night, we tested with like 5 people. So
Freaking out.
uh-oh.
What am I looking at, Syed? What is this?
Okay, so you know how like oh my god, there's a lot of people. Okay, I mean that's a good sign, right? Like you guys did a good job. Okay, so you know how we were looking at this graph, and there's a detection event. So each one of these dots is like a qubit. Like we are all now qubits on this plane. And so we are now going to run through the algorithm as if we are the qubits, and we are running through this algorithm. So I'm going to run this. Damn, that's a lot. I don't even know what's going to run now. Okay.
I like that.
Okay, so you should see now on your phone that it says enhanced Blossom algorithm running. And you'll see that now it's creating paths between all the nodes, surprisingly, with all these people. And so what's happening right now is this process that you see up here where this algorithm is actually going through and doing these steps. And so just like this is a very small number compared to what Trevor was showing before, which is 1 million qubits. So imagine this graph at 1 million, right? And that's like one of the biggest problems. And you want to do that like at microseconds. And so we're running this process to find errors, but this is taking us like a minute. So that's one of the biggest challenges, to do that error correction. So I guess I'll show it on the screen.
Get your oral away from me.
Yeah, so it's just running through the algorithm. I guess Trevor, do you have any
Very
comments?
sick.
Yeah? Do you have any comments on
Very
this?
sick.
Yeah. Did anyone have any questions while we're doing this fool's errand?
Yeah.
Go ahead.
Showed me like the squares on slide number 6. You said measurements around the qubit. What is that?
Sorry, where?
Slide number 6, the previous slide.
So,
Yeah.
nodes here?
So no errors detected.
Yeah.
You said in the center there's the qubit.
Yeah.
You said measurements around the qubit is what demonstrates what is around it. What does that mean?
I think Trevor can give like a scientific answer.
Oh shit, okay, yeah. So everyone here is kind of representing a qubit, so it's a bit of a loose analogy, but it's sick. And so in error correction, they'll run measurements and they'll get like pairs of like ones. So you have a pair of ones, and that between those ones, all those qubits errored. So you're looking. So the Blossom algorithm finds what's called a minimum weight perfect matching. So it looks for pairs, and pairs such that their distances are very close. Because if things errored, they probably are close together. Like the errors are probably close together. That's kind of the assumption. And so you want that distance small. So it kind of looks for these matchings of errors that are close together. And it's the fastest known algorithm to do this. It is a classical algorithm, not a quantum algorithm, but you need these decoders running simultaneously as your quantum computer is computing, just decoding errors. So these decoders are run on normal computers, transistor computers, while the quantum computer is computing. And it's running algorithms like this, just the correct errors. And it needs to run as fast as the quantum computer. So like microseconds, nanoseconds, depending on your design.
And just to add, like you're asking about like what do these measurements mean? Like if you're stepping through a quantum algorithm, there'll be like gate operations and there'll be a measurement operation. And so like when you're doing, let's say you're doing like a bit flip, then you're gonna measure the result of that bit flip. So this is like the measurement of what that qubit should be, like the state of that qubit. Is that like pretty accurate, right? Yeah. You had a question?
So this seems like a lot of like effort and investment. What are the practical like applications of a system like this?
Dude, is your marketing clearance for this?
Oh shit.
Yeah, like, what do you do? Yeah.
I think we can give a general answer that's not related to our company, not backed by our company.
You're not promoting Syed Quantum today. Talk
Yeah,
about
exactly,
just
yeah.
about quantum computing.
I guess like applications. What do you think, dude? What do you think?
Or
Yeah, take a hit, dude. Take a hit. Take a hit. Yeah, take a hit.
So, well, I'll give. Yeah, you snagged me. Yeah. So originally, Feynman, who theorized them, he wanted them for quantum chemistry, which sounds like, oh, that's weird. That doesn't sound super useful. But quantum chemistry is behind like everything. So battery design, pharmaceuticals, agriculture, like everything is quantum chemistry almost. And so anything that requires simulation of quantum mechanics is exponentially sped up if the underlying computer is quantum mechanical. So that's the first application. That was what they were originally theorized to be. Then some like super geniuses figured out with this like crazy computing device, you can do some crazy shit. And in 1994, this crazy guy, Peter Shor, who could win a Nobel Prize, figured out you can break encryption with it, RSA encryption. And so RSA encryption's behind Bitcoin, it's behind your Facebook password, and no one thought it was crackable. And you could crack it. He proved it in theory. If you have a quantum computer, fault tolerant, no one has it, of around 3,000 qubits. Logical qubits, so millions of shitty qubits, you can crack RSA encryption. That is massive, so that really took it off. Because like now there's like, oh, what can you do with this thing? Like you can break encryption. No one thought that was possible. And this is like the most mainstream encryption method. So like if you, it's in Bitcoin. So your public key and private key in Bitcoin is RSA. So
is it like
I can
developing a
tell you,
weapon?
yeah.
Is it almost like developing a weapon, or?
Yes, yeah. Oh, yeah, there's defense, 100%. Yeah. But the normal computers used as a weapon, so it's like when you can use it as a weapon, people start investing a lot of money in it. So
it's a weapon. It's a weapon.
Yeah. That's the only reason, but the normal computer is a weapon too. So,
Yeah, technically, right? Like drones.
Yeah, 100%. Like it's like the normal computer will always be the biggest weapon. Like
You open your mouth, like,
oh
closer.
shit! Yeah. Sorry, it's not even on. Does that kind of answer?
Yeah, and just to add on to like what he was saying, like from the scientific applications, I think one thing that I find interesting is with quantum, you are working with probability, and you're not doing that conversion between discrete outputs and probabilistic outputs, and so you're just getting a distribution out the gate from a quantum computer. Right now, like what we do with a lot of studies is like we take a discrete output and then we put it into a probabilistic model, and so there's always that translation that happens. And I think with quantum, you take out that translation step and you get probability out the gate. He had his hand up. Actually, no, he had his hand up first. Yeah, there he is. Yeah, sort of. Do you want to come up here?
You can hear me, it's fine.
Okay, sure.
So Microsoft made recent headlines with their new chip, the Marker or whatever.
Maharana.
Yeah. Where does that fall on your scale of good qubits to shitty qubits, and how is that process?
That's a good question.
Should I take the hit?
Yeah, take a hit.
Okay, I'll take the hit. Okay, so the industry. So first of all, Microsoft invests in us, so that's how. Kind of. Oh yeah, so that's how kind of how much they think about themselves. They invest in us. So they apparently have a bunch of people that are after the Nobel Prize trying to make this topological qubit state, but they don't really care about quantum computing. They just want to make this weird state. Have they made it? No. And that's kind of what's their state. So they're kind of behind a bit, like Microsoft. I'd say like my biased opinion is that we and Google are at the top of the ladder, but that's my biased opinion. Microsoft, is doing good work, but they have a bunch of people that care more about kind of a state of matter, which is underlying their quantum computer, than the actual like thing itself.
Yeah, I feel like they're trying to solve like two hard problems. Like already getting a quantum computer is really hard, and then they're like, let's find a new state of matter at the same time.
Yeah.
It's like, okay, it's two hard things. Dude.
I don't know if that answers it, but yeah, that's kind of.
One more question.
Okay, one more question. Dude, you do it, man. I chose the last two.
Oh, I don't know. Well, this guy's been begging. Okay.
I'll throw out the. I'm definitely gonna throw out maybe a semi-dumb question. See, I don't want to ask what is an error because I guess.
Yeah.
But I'll ask it in a different way.
Yeah.
Which is to say, as I understand an error, usually you have like a target or a goal in mind, and it's not hitting that.
Yeah.
So like, what is an error in this context? In the sense of like, what's it actually trying to do, and what's it failing at in that process?
Yeah.
Because I don't know, maybe I missed that step, so caused like a gap in my understanding. So if you guys could, yeah.
Okay. You want to?
I'll do like a very like basic answer, and then you can do a complex one, I guess. I mean, there's an expected output, and so like we know, in a simulator that there's an expected output, and so you know that if you're not meeting that expected output, there's some error along the way. Not saying that this is the solution, but that just shows that an error exists. And I guess your so I understand your question correctly, are you saying like, why does this find the error? Is that the right question? Or?
No, my question is like, what is the actual output you're expecting? And then from that deriving that this is an error or that's an error.
Are you familiar with like programming or?
A little bit, yeah.
Yeah, so like imagine you're like, I want to do one, this is not even programming. If I want to do 1 + 1, it should equal 2, right?
Yeah.
So imagine I did the plus operation and it gave me like 3. So it's like obviously 3 is not 2 in that case, so that's an error.
Is there a specific application in mind, like for quantum computing, or it's as broad as 1 plus 1 equals 2?
I mean, we want things to be true, I think in general, right? Like, whatever we do, we want the answer to be right. But I guess, Trevor, I'll give it to you, man, the answer is
No,
yes.
it's good. Yeah, no, it's like you can compute 1 plus 1. If there's adders, there's quantum adders, so you can literally compute 1 plus 1. And if it doesn't give you 2, like that's like pretty shitty.
Okay.
But yeah, it's like an error is like, you know that slide with the 1, 0, 1, 1? Like if one of those 1s is 0, that's an error. Like it's like just that simple. It's like literally like one of the bits is, one of the qubits is like not holding correct information, and anytime there's like an interaction with that like trapped atom or whatever your design is with like the external space, you'll get errors. Like it wants to not exist in that isolated cold state that it's in.
And also to add, like, errors exist in current computers as well. Like, we have like DIMM errors, we have like hard disk errors. We just don't notice it now because it's like a mature technology, but like floppy disks or like hard disks used to go corrupt all the time, right? That's like a form of error as well, where like sectors are having wrong bits. So.